A user clicks Place Order. Behind that click, your checkout service has work to do. It reserves inventory. It sends a confirmation email. It logs an analytics event. It kicks off shipping. 4 side effects, all fired synchronously, one after another. Most of the time, it's fine. 200 milliseconds, user sees success. But today the email provider is slow. 2 seconds, 3, 4. Your user is still staring at the spinner because checkout is politely waiting for the email library to finish. The database is fine. Your code is fine. One slow downstream dependency has frozen your entire checkout. This is the synchronous trap. Your checkout endpoint only moves as fast as its slowest side effect, and you have 4 of them. In the next 10 minutes, we'll see how a message queue cuts that cord, and why it's the backbone of nearly every scalable backend. Here's the fix. Instead of checkout calling email, inventory, analytics, and shipping directly, it writes a single message to a queue. Order 47 was placed. That's it, one line, durable, somewhere safe. Checkout returns 200 OK in 40 milliseconds. The user sees success. Meanwhile, on the other side of the queue, 4 independent services are each pulling messages and doing their own thing. Inventory decrements stock. Email sends confirmation. Analytics logs the event. Shipping creates a label. Each of them takes as long as it takes. 100 milliseconds, 2 seconds, it doesn't matter. Nobody is blocked on anybody. This is the core idea. The queue decouples the producer from the consumers in time. The producer is fast. The consumers can be slow. The queue absorbs the difference. Now, what's actually inside that cylinder? Let's look. Zoom in. Inside the queue is a broker, a process whose only job is to accept messages and hand them out. The data structure is almost always the same, an append-only log. New messages go on the end. Each gets an offset, 0, 1, 2, 3. Once written, never modified. Why a log on disk and not just a list in memory? Because if the broker crashes, you can't lose your orders. The message has to survive a power loss. So every write is F-synced. And in production, that log is replicated across 2 or 3 broker nodes. A message isn't considered committed until a quorum of replicas has it on disk. Only after that commit does the broker say, "Got it," to the producer. That's the durability contract. You wrote it, we've got it, we won't lose it, even if a machine goes down tonight. So the producer side is durable. What about the consumer side? A consumer pulls message 47 off the queue. It processes it, sends the email, writes to the database, whatever. Then it calls acknowledge. I finished message 47, you can move on. The broker advances this consumer's committed offset. 47 is done. Next time, it hands out 48. But what if the consumer crashes midway? It pulled message 48, started processing, and then the process died. No ACK was ever sent. The broker waits. The ACK never comes. After a timeout, it redelivers 48 to another consumer. That's the rule, no ACK, no deletion. The broker never drops a message just because somebody took it. It only drops it when somebody confirms they handled it. Which sounds great, until you realize it leads directly to our next problem. Because of that redelivery, you have to choose what you want. There are 3 options, and they are not equal. At most once. The consumer acts immediately, then processes. If it crashes mid-process, the message is just gone. Fast, simple, sometimes wrong. At least once. The consumer processes first, then acts. If it crashes after processing but before acting, the broker redelivers. The work runs twice. Nothing is lost, but some things happen more than once. Exactly once. What everyone wants. Every message, processed exactly once, no duplicates, no losses. In the strict sense, across a network with crashes, it's provably impossible without coordination. What people usually mean is effectively, once. At least once delivery, plus an idempotent consumer, one that recognizes duplicates by some message ID and skips them. That pairing, at least once plus idempotency, is the pragmatic default for almost every real system. One queue, one consumer, fine for 1,000 orders a day. But 1 million, you need parallelism. The answer is partitions. The broker splits the topic into independent shards. Our order's topic has 4, P0, P1, P2, P3. Each partition is its own minilog with its own offsets. Now we create a consumer group, let's call it order workers. 2 consumers join. The broker hands partitions out. C1 owns P0 and P1, C2 owns P2 and P3. Both work in parallel. Add a third consumer. The broker rebalances. Now each consumer handles fewer partitions and throughput goes up. One important rule: inside a group, each partition is owned by exactly one consumer. That guarantees ordering, messages for the same key always go to the same partition, and that partition is processed by one worker in order. Parallel where you can, ordered where you must. Redelivery sounds great, until one message is simply broken. Imagine message 84 references an order whose customer record got corrupted. Every consumer that picks it up throws an exception. The broker redelivers. Another consumer picks it up. Same exception. Without a safety valve, you've built a perfect poison pill. One bad message blocks every message behind it forever. The fix is a dead letter queue. After a bounded number of failures, say 3, the broker stops redelivering. Instead, it publishes the message to a separate queue called orders.dlq and acts the original. The main queue keeps flowing. Message 85 gets processed, then 86 as if nothing happened. The DLQ becomes your inbox of problems. An engineer looks through it later, fixes the root cause, and either replays the messages or discards them. Don't block the whole line for one bad message. Almost every message queue supports 2 fundamentally different delivery patterns. It's worth being able to tell them apart. The first is point-to-point, also called a work queue. One message goes to exactly one consumer. If 3 workers are all pulling from the same queue, each message is handled by whichever worker grabs it first. The others don't see it. This is what you want for tasks: resize this image, charge this card, where the work only needs to happen once. The second is pub/sub, short for publish subscribe. One message is copied to every subscriber. If 3 services are subscribed to order events, all 3 get a copy of every order. This is what you want for notifications, where multiple systems independently care about the same event. Same broker, often the same message, completely different topology. The distinction isn't technical plumbing. It's about intent. Do you want work split, or do you want everyone told? Let's map these ideas to the tools you'll actually see in production. Kafka, log-based, partitions and offsets exactly like we drew. Built for very high throughput and the ability to rewind, you can replay any offset from hours ago. The go-to for event streaming and analytics. RabbitMQ, classic broker with a rich routing model. Exchanges, bindings, routing keys. Good when you want flexible patterns like deliver to any queue whose name matches this wildcard. Lower throughput than Kafka, but much more expressive. Amazon SQS fully managed, no broker to run. Durable, infinitely scalable, dead simple API the trade-off. By default, there's no ordering guarantee, messages can arrive out of order. Use it when you want the queue to just exist. NATS, lightweight, low latency, cloud native. Excellent for pub/sub and service-to-service messaging where milliseconds matter. Same fundamentals underneath. Different trade-offs in throughput, ordering, routing, and ops. So here's the whole picture, in 5 words. Produce, persist, deliver, ack, retry, or dead letter. That chain is what a message queue gives you. The producer is never blocked on a slow consumer. The broker never loses a committed message. A crashed consumer gets its work redelivered. A poison message gets shunted aside so everything else keeps flowing. The headline: a queue decouples 2 things at once. It decouples time. Your producer runs fast, your consumers run when they can. And it decouples scale. You can add consumers to a group whenever you need more throughput, without touching the producer at all. Almost every scalable backend hides one of these in the middle. Now you know what it's doing. If this helped, subscribe for more state and flow explainers. Next video, another piece of the system design puzzle.